Okay, this is definitely a work in progress. We're still in early stages of this approach. And I have a lot of motivation here and a little bit of solution, perhaps. So, over the years, we've had quite extensive experience with large biological data sets, and I'll show you a little bit about that. And what we found is that typically the data storage and access is just as big a problem as the computation, especially these days with GPU support and so on, when you can get tens of teraflops for $10,000. It's the storage that is the bottleneck. So we need to support a variety of data types that will be processed in our cases by a combination of human and computational methods. And especially with the human in the loop, we need to keep these data online for long periods of time, because you do not get an exact solution or a consistent solution in one step, and there are still parts of the analysis that have to be done visually, and so that takes a long time. This is a little bit different than a typical supercomputing application, which tends to load up a lot of data. You do your computation, you get the answer, and then you remove the data. Here we need to keep the data. And item number 3 here, allow incremental refinement of the mapping of the data and analyses as they go forward. I'll explain more about that. In short, we need a new approach to this. And so my idea to this was what I think of as a virtual volume file system approach. So as most of you know, in Unix and Linux land especially, everything looks like a file as far as the input-output to programs. So the notion here is to produce this file-compatible approach, and there's a mechanism called fuse that I'll discuss in a minute, that allows us to dynamically produce things that look and behave like files for the most part, but allow you to dynamically produce the content for these virtual files. And a very important item here, bullet number 3, we need to reduce the need for redundant data storage. So when refining these various models of the 3-dimensional structures that we're interested in, we never get it quite right, but the researchers, of course, are anxious to get started on whatever you have at the moment. And so you need to preserve both today's model and tomorrow's model and the next day. And if you're working with, as we are now, tens to hundreds of terabyte data sets, pretty soon that 10 to 100 terabytes, when you multiply it, it just grows out of all possibilities to support it. So let me go back in time a little bit here and illustrate how we got here. Back in 1988, 1999, we got involved with the Visible Human Project, which at that time, the roughly 30 gigabytes that fits on your thumb drive now of data for the National Library of Medicine Visible Human was a big storage problem. And so Stu Pomerantz, a fellow who was here at the time, and I developed this thing that we called the PSC volume browser to allow students at the University of Michigan, in fact, accessing data from here at the PSC to see views like shown here in a static view on the screen of the visible human data, which is shown here in 2 forms: a cut plane view. Realize this is a volumetric data, so we're just showing an arbitrary 2-dimensional plane, and it looks a little weird because I've intentionally cut it out of the original data capture plane, and also it's not the frontal plane and so on, just to show that we can do arbitrary cut planes. And then on the right, we have various segmented structures and so on that go along with this. So this was used for teaching in the anatomy classes at the University of Michigan. Then we went looking for other sorts of things that we could do with this technique that we had developed. And we went to all sorts of volumetric data and time series data. That's the beating heart there from a CAT scan, a mouse CAT scan. This is not the exterior of the heart, it's the blood pool in the left ventricle in this case. So we developed some special analyses and then continued to look for big data problems. And I met a number of people in the connectomics area. So I know that your work is not exactly what we think of as the extreme connectomics, but you're more interested in individual synaptic junctions or smaller regions, as opposed to this massive sort of thing that is typical of connectomics. But I just want to show here at the bottom sort of three ranges that people use the word connectomics to describe. And at the left, tractography, the view of the white matter in the brain, is sort of missing what I think in electrical terms as the transistors, the gray matter that actually does the computation. So this is just the long-range wiring. And it has a fairly low data density, so that an entire human MRI, which has the great advantage that you survive the procedure, right, has about 10 megabytes for an entire volume. The next levels of resolution, which you would not survive, okay, and are therefore not candidates for anything except research studies, optical level in the middle. Brainbow is a word coined by Jeff Lichtman and team at Harvard. Gets us to a range of about 10 gigabytes per cubic millimeter. Now the human brain is about 1,400 milliliters, and cubic millimeter is 1,000th of that. So we would need a huge amount of this data to cover the equivalent of a human brain, but this is quite nice for mouse studies and things like that. Now getting more to the area that you're interested in, serial section electron microscopy reconstruction, which Greg Hood in the back there and I have done quite a bit of alignment on this data over the past, I don't know, almost 10 years now, I guess. We get down to a level where we need 3 to 4 nanometer resolution, which unfortunately we cannot capture equally in all dimensions due to the physical sectioning. But we get a data density of approximately a petabyte per cubic millimeter. Nobody has really done quite the petabyte yet, but we're creeping up on it. And of course, we can look at this data in many levels of detail. So at a very coarse detail, the rectangle on the upper left is about 1.25 millimeters tall. And the big openings you can see are capillaries. So the smaller of those capillaries are about 7 microns in diameter, just big enough for one red blood cell to go through. They go through their single file. And so the rest of this is a series of zooms until we get down to the level that you're primarily interested in for seeing things like synaptic junctions. And the connectomics folks especially, and for your cell modeling, you're interested in producing geometric structures, 3D geometric structures from this. So I won't tell you entirely how to do that. I'm just addressing some of the data handling issues. Now, when we get this data, in this case, this is a C. elegans from a fellow named Rick Fetter, one of the world's best electron microscopists. And Greg aligned this particular data. This is a C. elegans inside the egg yet. So it's about 40 microns in width, I believe, and consists in this case of about 700 sections. So you can see the value of registering this in being able to go from not seeing anything except the curve of the worm, and I guess this is flipped, but to getting some useful structure here, at least being able to see cell nuclei and so on. Now, this is a much larger scale than what you would want. The stuff around the upper periphery there, by the way, are E. coli bacteria, just to set the scale for you. Anyway, you never get these alignments entirely right in one shot. It's an iterative process. And even though we've been at this for a while, we are trying new algorithms and so on. And we end up with a proliferation of data files. As I alluded to a minute ago, you start with 10 or 100 terabytes, and you make your rendition of the day, which is another 10 or 20 or 100 terabytes. And then you improve that, and pretty soon you're multiplying this out some number of times. And also you have various applications that are processing this data for the purpose of segmentation or other analyses that you would like to do. And often they have slightly different formats that they require and different access patterns and so on. So you start with a single data set, and the conventional model is that you produce some number of intermediate data sets that go to different applications. And this works, but even here at the supercomputing center, when you get to hundreds of terabytes of data storage, you really don't want to replicate that any more than necessary. So we need a new approach to scale up that lets us avoid storage duplication. So what we would like to do, at least for Greg and I, is produce these registration, these alignments, to produce a coherent three-dimensional volume in a way that users can see the proper alignment, but that we only need to store the original data once. Now, the processes that Greg and I use for alignment are computationally intensive and may be done outside the pipeline that I'm describing here, but the end result is a series of deformations to the original images, and that's what the user wants to see on their screen, or that we want analysis programs to process. And of course, seeing things for human view is one thing. You might have a specialized viewing program or something like that. But when you have segmentation programs, they often expect to see aligned images as TIFFs or some other file stack. So they expect to be able to read files. And so looking forward here, which is the real gist of this, at the 100 teravoxel or so level, which we're at in the last year or so, this still only represents 1/8,000th of a mouse brain. So it's pretty small, literally grain of sand type of stuff. And the next big target, as people have been saying for roughly 5 years now, is to get a cubic millimeter, which would be more than a petabyte. And a few people are starting to think about imaging a full mouse brain, especially in a couple of the German labs. And that would be on the order of an exabyte, 10 to the 18th bytes, which none of us, even at supercomputing centers, are really ready to handle that, especially if you talk about taking 10 to the 18th bytes in, producing a 10 to the 18th byte registration, and then finding, oh, there's problems with that, so we want another one and another one and another one. You just can't do it. And then, of course, the long range, a human brain is 1,500 times that. So to keep this...
Is that a Yada?
Yeah, it's a Yada bytes.
Yada bytes.
It really is. That's the name. Somewhere out there is Bronto bytes. I forget what that is. Or molabytes, 10 to the 24th. 6. So the virtual volume data model, I think of it as a virtual volume file system. The notion is to use this thing called FUSE, File System in User Space. So for those of you who are computer-oriented, you have the operating system kernel, which runs in sort of a privileged mode and has direct access to all the hardware and so on. And then you have user land. So you write your Hello World program. That's running in user space under all the restrictions that apply to you, the user, so that you can't interfere with other users or damage the system or whatever. So the FUSE mechanism allows us to write programs that generate things that look like files but aren't really, but that allow other programs to access these files without really realizing that they're calling the virtual volume file system. So for those of you in Unix land, you're probably familiar with pipes, where you pipe data from one program to another. So that gives a limited sort of file equivalent access in terms of one directional data flow. And there's actually a way to get two directional data flow, but there are lots of limitations to pipes. You can't send more than one chunk at a time. Programs have to understand the format of the data going through the pipeline, and you can't seek. That is, you can't do random access on a pipe. It's just a one-directional stream. Whereas with real files, even something as simple as a single TIFF file, you have to do seeks because of the way the data is structured with directories inside the files, and you have to jump around inside the file in order to understand it. So the advantage here of this file system approach is that it allows us to support all those capabilities that would be missing with pipes or other types of mechanisms, and allows us to put active computation and analysis into the data pipeline. So as I mentioned earlier, we have huge amounts of computational capacity, but the storage access, just the sheer storage and the bandwidth, are often the limitations. So every time you go get the data, you would really like to have the opportunity to do some computation with it. And so that's part of the purpose of this VVFS, to do computation as you're accessing the data. So let's think briefly about what a file system is. It is simply the storage arrangement, the file structures that map file names to the actual contents, typically the locations of the data in terms of disk blocks. Also data about modification times, permissions, ownership, and so on. And when you have multiple disks in a conventional system, you would typically mount a disk or a multi-disk file system to a particular directory. We want to do the same sorts of things with the virtual file system. So the advantage of, or one big advantage of this virtual volume file system approach is that unlike the days when we would write file system drivers in the kernel, and you would write your program, and then you have to reboot the system and try it out and find the flaws, and a very difficult thing. The file system in user space allows individual users to go through their debug loop as many times as they would like and not affect other users. So that's this business of separating the safe parts of the system inside the kernel and letting the user do whatever they want on the outside. So from a system admin point of view, this lets users do things that they would not trust you to do if you were writing conventional kernel-based file systems. So when a program accesses a file, it makes a system call, typically open, close, read, write, things like that. And in the case of Fuse, the kernel figures out that your program is issuing this call to something that is mounted as a Fuse file system. Your program doesn't need to know this. It just accesses files. And what the Fuse kernel module that's already there does for us is it forwards the request back to the program that implements the virtual file system. So when you're writing one of these Fuse file systems, you're really writing an ordinary user mode program. It's just that what it has to do is sort of a event-driven computation that implements the roughly 35 possible file operations. Usually we don't need all 35, so 4 or 6 or something, read, write, open, close, and seek are the most essential ones in order to make a functional file system. And if I have time, I'll show you a tiny little demo here at the end. So here again, some of the essential system calls. We don't need very many in order to get basic function. Now, when we're aligning data, Greg and I use different methods, but nevertheless, we end up with some sort of a representation of the deformations. In my case, I use a triangulation mesh, and this is showing a cross-section through a zebrafish head, and in its original form here, and then just for graphic display here, showing the triangles and bringing this back into sort of a rectified view. And so the description of that are all these numbers on the left that describe the position of the triangle vertices and so on. This is the data that would change if I go from today's registration to an approved one tomorrow, or maybe I need a lot more triangles. Typically, this is just a handful to show you the example here. But just to understand the scale of the data, I'm showing it on the screen here at very small scale, but the fish head that I worked with most recently here is on the order of 10,000 pixels square, 10 to the fourth times 10 to the fourth. So it's a 100 megabyte image in its real form. So there's a lot of detail that you can't see, but at least at this scale you can recognize that it's a fish. So the notion of the VVFS is much like the earlier diagram. We take in the raw geometric data, but the virtual volume file system then dynamically will restructure this data and deliver it in a file-compatible form to all of the same applications that you used before. It's just that you're not using all of that storage. Now, of course, there's a trade-off, because now you have to dynamically compute certain things, maybe repeatedly. But we're computation-rich and storage-poor, relatively speaking. So it's a good trade-off for the most part. So underlying all this, since we're dealing mostly with three-dimensional data, we need some sort of a spatial organization. And if any of you are familiar with conventional file systems, this looks very much like what we use in Unix. I say Unix because I'm an old guy. I got my first Unix tape in 75, I think. So these spatial nodes, as I call them, that sort of blue block in the middle, is analogous to what in Unix land is a one-dimensional file structure called an inode. And the pointers out of the inodes in a conventional system point to the actual disk blocks. Whereas here, we're building on top of other file systems what we would have in the spatial nodes that would allow you to do three-dimensional access directly, then would be a pointer to where the source data is and some sort of transform. So think of those triangles that were moving around previously. That's what the transforms would be. So fetch the data, apply the transform, instantiate that region, and then the user mode program that would be analyzing to do segmentation or whatever would seamlessly see the results of all this. Now, clearly there are several problems. One is that you could be requesting some little bit of data in the transform space that requires, some humongous analysis that would take days to perform. We can't solve that problem for you, okay? So this is, trying to resolve a typical problem that we would see in terms of having previously analyzed the data as Greg and I do to produce the right file mappings, but then produce the right results. And then you could go back to last week's version or last year's version or whatever you would like to compare results. So one of the important things that's developing and that we're trying to take advantage of is GPU computing. And now with the NVIDIA P100s, for $10,000, you can get roughly 22 teraflops worth of compute power. Just an incredible amount of compute power. So there are a lot of things that, when I mentioned a minute ago, you might be accessing some bit of data that requires an immense amount of computation. At least in my terms, from starting with 100,000 operations per second computers to now, we can really put an immense amount of computation in the pipeline to do things like segmentation and so on, at least over local regions on the fly. Now, this is not achieved yet. This is what we're working towards. And one of the other keys to getting high performance here is to avoid disk latencies whenever possible. And of course, you're all aware that flash memory now is giving us much faster access times. Even in cases where the bandwidth is not improved, we get much faster access times. And for a lot of the three-dimensional access, that's very important for us. So let me break out of here and just give you a trivial demo to get the idea here a little bit better. So I apologize, I don't know how to make the font bigger there. I'm just going to ls minus L, something called mount, MNT. It's a directory that's just sitting here in this position. And so what I'm going to do now is I have run VVFS01, my initial version volume, virtual volume file system, mount, just like you would mount a remote disk or something like that. So now if I do the ls again, I see all these things that look like files. They aren't really. What's happened, that virtual volume file system has read in one volume of data that represents, in this case, a little section of visible human head. So now this program that I'm using, CaMKII, Quick Image Viewer it's called, knows nothing about the virtual file system. You know, it's just made to image files and often put it into this sort of movie mode where it's not producing a movie in an MPEG sense or anything like that. It's just going through the files real quickly and displaying them here. So in this case, we're getting a side view, sagittal view through the head. And if I do the same thing here to QIV MNT / Y asterisk, now I'm going in a different orientation. So it's recomposing. These images did not exist on disk directly. They're being composed on the fly through this fuse-based file mechanism. Now, one of the other things we can do here that I've been playing with is sort of how to steer computations. So let me start this again. KV. So I know you can't see this here, but the QIV has a mode where it looks for modifications to a file. So I have one particular file here that I just call images.ppm. And the notion is that in the virtual file system, I've also implemented something I think of as a control file where I can send commands into it. And I know you can't read this down here, but I'm just sending in different orientations and some other commands here. So let me run this. And you'll notice that the display is changing as it gets each of these commands written to the control file. So the invert intensities, for example, there. And this is interesting because one of the problems that one has here in this virtual file concept is that the number of virtual files you can produce is essentially unlimited. You know, any little increment of tilt or anything. So if you passed all these requests in to give all of that information, what do you list in terms of a LS, you know, a directory listing? Do you list billions of files? Well, that's not practical. So I'm thinking of this control mechanism here as a way to pare down. You know, maybe you get an orientation through a volume and then you say, okay, show me the 1,000 positions in front of or behind that or something like that. So this is still a work in progress in that idea. But at least this little demo shows that the fuse mechanism works for doing the sorts of things that we're interested in here. And so if you have Blender or something and it wants to look at one of these files, hey, that's fine. Blender wouldn't know. Okay? So that's basically what I wanted to say.
Well, if I sit proudly, you can hear me, but yeah, CaMKII is calcium calmodulin dependent kinase type 2. And it's one of the, oops. Yeah, it's one of the main drivers of the NMDA-dependent synaptic plasticity, and it is a very highly expressed compared to other kinases, at least 10 times in the brain. And more specifically, it's structurally very complex. It's not like the kinase or phosphatase as we talked in the morning session. It's a kinase with 12 subunits. It's a dodecameric kinase. And actually, there are some new studies there also showing that it could be in tetradecameric form. And it has multiple phosphorylation sites, and then it has binding sites for calmodulin, et cetera. So it's quite a complicated molecule for the modeling. So the way we model is we assume that, well, this is the way that we approach the CaMKII. This is the inactive form. This is a dodecamer. It's like 2 rings on top of each other, and then there's each of them is a one single CaMKII subunit. And each subunit has a kinase domain and a regulatory domain, and then there's a linker between those two. And on this linker region, there's a phosphorylation site, which is T2 305 or 306. So there are 2 of them right next to each other. And for the modeling purposes, we just use them as one. And there's another autophosphorylation site, which is this 30286. And if there's a calcium calmodulin binding to the CaMKII, this will get activated. The kinase domains will open from the regulatory domain. And this is the first active form with calmodulin. But eventually, after the phosphorylation, this calmodulin can unbind, but still the CaMKII remains active because of this T286 phosphorylation. And that's pretty much like how this calmodulin is coming, and then it's binding to the linker part, and then this is 286 phosphorylation site, and then after it's unbind, this 305 could also get phosphorylated, or 305, 306. They're right next to each other. And when we are doing the modeling, we are more focused on this calmodulin binding, 286 phosphorylation, and 305, 306 phosphorylation. And since they are close to each other, we just think them as one single site. I mean, well, this is actually a model from Leslow's lab from UCHC. So the way they assume the system is that it's like a ring. There are 6 association domain and 6 kinase domain. And then the linkers are between them. And then for each subunit, they assume there are 6 states. And the states are based on calmodulin binding, T286 and T305. And in the beginning, you're starting from this state, which is called DUU, which is T286 is unphosphorylated, 305 is unphosphorylated, and calmodulin is unbound to the system. And it could go to a basal phosphorylation, and then the 305 could be phosphorylated, which is very slow. We are not considering this one as an important part of this system. But this 4 calcium-bound calmodulin can bind to this unbound CaMKII, and then it will make the first active state, which is pretty much this one, when the calmodulin is binding to the CaMKII, it will make it activated. And then that state is called CU in this case. And after this calmodulin binding, this can phosphorylate, and it will go to the next state, which is CP. I mean, by phosphorylation, what I said is the T286 can get phosphorylated, which is the main activation mechanism. And afterwards, this calmodulin can unbind, but still it will remain active, and this state is called DPU. And also at this state, it can also phosphorylate at T305 site, and then it will go to another state, which is called DPP. So in total, we have 6 different states of CaMKII. I'm not talking about the states of the calmodulin or calcium, et cetera. Is that clear? I guess many of you know this model, but and of course, there's this calmodulin binding and unbinding could be in 2 ways. One of them is all calmodulin with 4 calcium on it can just leave the CaMKII, or a calmodulin with 2 calcium and 2 free calcium could be released from the CaMKII together. So this is another mechanism. And I think the most interesting thing that I want to explain, and then we can implement using BioNetGen, is how this Cu to Cp phosphorylation works. Because that is called inter-subunit phosphorylation. And it is happening like each neighbor subunits are affecting each other and changing their phosphorylation rate. So basically, if your neighbor, let's say, since it's a ring, if your left neighbor is in Cu state, it has a different phosphorylation rate for you. Or if it is in Cp state, it's a different phosphorylation rate. Or if it is in dpp or dup state, it has a different phosphorylation rate. The DUU and DUP does not have any effect on the phosphorylation, but the other 4 states have different rates of phosphorylation for each other. I will show you how this will be done. But I just want to show you in the beginning like some simple rules, and then we will just get to the BNGL code, and then we will see what are the rules, what are the molecules, what are the strategies that we are dealing with. And in the beginning, I just want to show you this model as like, I want to make the model as dimer first, like the simplest form, and then we can just increase the size of the ring by making trimer. If you want, you can make it a hexamer, etc. And then at that point, we need to use NFsim. So let me go on. Yeah, so this is like a very simple reaction that we have. We define our calmodulin has 4 different calcium binding sites. And each calmodulin has 1 CaMKII binding site. And these are our calcium molecules. It has a calmodulin binding site, and then they could just bind to each other. Right? Simple. This is rule visualization. We will have also some tutorial sessions for them so we can see them. Or, for example, this is another calmodulin. It already has 2 calcium bound, and then we are getting 1 more calcium binding to this 2 bound calmodulin. Of course, we can talk about the cooperativity, and then like there's a different binding size, etc. But this is the simplification that we have. Or, for example, this is another rule. This calmodulin has 4 calcium bound, and the CaMKII binding site is empty. And in the CaMKII, both T286 is unphosphorylated, and T305 is also unphosphorylated. And then between those 2 sites, there will be a bond formed. So it's the calmodulin binding to the CaMKII in the unphosphorylated form. Or, for example, in this case, again, the calmodulin binding to the CaMKII, but the CaMKII, the T286, is in the phosphorylated form. So basically, this one is the reaction happening over here, and the second one is the reaction happening over there. The difference is the binding rates are different for these 2 reactions. And yeah, so this is the, what is that? This is the basal phosphorylation, because our T305 is going from unphosphorylated to the phosphorylated state, and the T286 is unphosphorylated, and the calmodulin is empty. There is no calmodulin in the CaMKII complex. Okay, just simple rule visualizations. And this is how this entire subunit phosphorylation works. For instance, there's this calmodulin bound to here. There's another calmodulin here, and then it can phosphorylate it. Or, for example, this doesn't allow because well, let me see. Yeah, well, this has calmodulin on it, and then if it is phosphorylated, it can phosphorylate this one. But if there is no calmodulin, of course, it cannot be phosphorylated. And the rule for this, for example, we got a CaMKII subunit here. We got another CaMKII subunit here. They are bound with some fictitious thing that we created since we want them to make it a dimer or trimer or hexamer or like a big ring. And since this is Cp, actually it's not CP, it's DPU because there's no calmodulin on it. And the T286 is phosphorylated, but T305 is not phosphorylated, so it's the DPU state is phosphorylating a CaMKII with a calmodulin, and the T305 is unphosphorylated, and T286 is getting from unphosphorylated to the phosphorylated state. Okay, so this is the simple rule visualizations, and let's get back to the hands-on part. So. Okay, if you will go to this bionetgen.org index PHP tutorials, or just go to the main page. Yeah, go to bionetgen.org, go to tutorials, and you will see that this CaMKII2 dimer.bngl. This is the model.
Sorry, I don't see how to get to it.
Oh, okay. Okay. Okay, main page. Bionetgen.org. Yeah. And then tutorials. In the tutorials, if you go to examples, the bottom one.
Are we just going to start out like commenting on any of these?
No.
Oh, okay.
Yeah.
Oh, we started with dimer. So okay.
Yeah, this is dimer. Okay. And if you click on here,
Should we download it?
you can download it, or let's do this. You can go to RuleBender. And let's start a new file. I'm sorry?
Is the file dated for
Yes, yes. I cannot get the same name.
Well, I think it still says 2nd June, at least online.
I mean, can you see the file?
Yeah, we didn't have the files here.
No, on the website, the files.
That's weird. Let's see. So the file is here.
Yeah, look,
You can't see the file, or? Yeah, I mean, it's updated very recently, so I'm not sure about the time, whatever time that the website shows at the bottom, but it should be updated. So, I mean, there's a very long parameter block in the beginning. So let's skip it for a while, and then let's go to the next parts. And then when we are dealing with the reactions, we need to see the parameters at that point, so we will come back to them. I'm just going to make this very large. Okay, as large as possible. Okay, so if you have the files, if you can copy paste, let's go over the code, and then I just want to talk about the molecule types. So what we have the calmodulin, and then it has 4 calcium binding sites. They're identical to each other. And then there's a CaMKII2 binding site, which is denoted as CaMKII. And we have a calcium molecule, which has only 1 binding site for calmodulin. And we have CaMKII molecule. It has calmodulin binding sites, which is CAM, the first one. And it has T286. It's the phosphorylation site. And there are two of, it could be in 2 forms. One of them is the unphosphorylated. The other one is the phosphorylated form. And there is this T305. It could be in UNP again. And there is this CaMKII6, which means this could dimerize. Because if you have 2 subunits, there should be a binding site between them. just to make sure that it's acting like a dimer. Okay?
So why 6?
I mean, normally, yeah.
There can be as many as 6.
Yes. I mean, well, no, not as many. In the dimer, there's only one. And also, there are some phosphatases in this system, that like PP1 or PP2A. There's some phosphatases, PP2, PP2A, or PP1. They are dephosphorylated CaMKII. And just for this purpose, we have this molecule PP1. But for the ESO simulations, I'm just going to keep it as 0.
I can't find that. Is that
Here, PP1. Yeah. And in the seed species, if you look at it, we get a CaMKII dimer. Normally, if you remember from morning session, we did not have complexes at the seed species section. But now we have complexes. For example, this is a complex. It has 2 CaMKII subunits. And then all of the phosphorylation sites are unphosphorylated. And then this CaMKII exclamation 1 and CaMKII exclamation 1 means those 2 CaMKII are binding to each other. Okay? In the trimer case, we will see a different example, and then I think we will understand it better. And we have calmodulins with empty calcium binding sites, and it's not bind to a CaMKII. And we have calciums, and then one additional thing, there is a $sign in the beginning. That means it's clamped, and the calcium number of calcium is not changing. Number of free calcium is always constant. Yeah, so it's clamped. It's not changing. No matter how many calciums getting into the reaction, when a calcium gets into reaction, there will be a new calcium molecule feeding into the system. So we are just keeping the calcium concentration constant. Okay? Yeah, it's not necessary, but for this case, and also like the number of calcium molecules is very high compared to CaMKII or calmodulin. So, I mean, it's not completely necessary, but it could be nice if you do it. What was the question?
Maybe should I go and find pop-ups?
Calcium and CAM is the same. So both are like at really high level.
Well, I mean, normally I'm running a parameter scan with calcium concentration. So it doesn't matter what parameter that I set in the model. Okay? Normally it's between, like, you can use like 1 micromolar, or you can use 100, or maybe more. It depends. Yeah. And in addition to that, I have a lot of observables. Some of them are not necessary, but for example, we are counting the number of every single state. How many DU, CU, CP, DPU, etc. Is this clear? And we are using this plus sign. That means it should be bound. There should be something over there. And I'm also counting the total number of CaMKII, total number of T286 phosphorylation or T305, and number of calciums, and number of phosphatase in the system. Those are observables if you're interested. I mean, if you're interested, you can always create more observables if something in interest. But for this case, I'm mostly interested in the phosphorylated one or the active one or the ones with the calmodulin on top. And we never used this one in the morning session, but there's also another thing called functions. If you want to use some different form of reaction rate, for example, Michaelis-Menten type, and if you are not sure about the mechanism, for example, if you go to literature in general, it is more likely you will find the Km and Kcat values more than the forward and backward reaction rates for the Michaelis-Menten. And if you want to make sure that that sort of reaction is required, just keep them. I'm not talking about them except the last two. Last two are pretty much giving you what is the ratio of the phosphorylated CaMKII at T286. If you look at the P is defined as how much of this CaMKIIs have T286 sites is phosphorylated, and then I'm dividing this one with the total number of CaMKII. And the second one, the phospho305, is another function. It's the P2, which is the T305 phosphorylated number over the total number of CaMKII. So basically, I'm looking at the fraction of phosphorylated T305 and T286. And the first three functions, this K off rate and the P rate. P rate is the phosphorylation rate, and this is the Michaelis-Menten total rate. This is KCAD times the PP1 is the amount of phosphatase over Km, the parameter that we feeding the system, and then all phosphorylated ones, the CP, DPU, etc. This is like the substrate for this case.
Why does the P and phospho have parentheses but the P2 doesn't?
It's my mistake. It should not be there.
Silent.
Yeah, it's silent, yeah. It's my mistake. It should be just P.
Okay.
Yeah.
So we could delete it and.
Yeah, you can delete it, yeah. Okay, so after functions, the most important part, in my opinion, is the reaction rules, of course. And the first 4 rules, let me do them multi-liner so that we can see them easily.
Jihan, is there cooperativity in this model? Calcium binding?
Well, there are papers of the calcium binding
There
cooperativity.
is. I see
Yeah.
the K-on and
Yeah.
the chaos are different for 0, 1, 2, 3.
Yes, they are different, and also like the parameters that we took from this paper, from the Michalski paper from 2012. It's in physical biology. I will give you the link at the end of the presentation. In that paper, all the parameters did not assume any symmetry. But in BioNetGen, you also need to consider the symmetry behavior. So what I mean by symmetry, because there are 4 calcium binding sites, and all of them are the same binding site, right? So there are 4, like for example, if you're a calcium molecule, and then if you're approaching this one, you can bind 4 different locations, right? So the rate you should define should be divided by 4. In their case, that they're just assuming that all binding sites are the same, and then they are not even multiplying with, they're just giving a number, which assumes that it binds to all 4 of them with a certain possibility. But when you're writing a rule like this, that means you can only bind to one of them. So basically, you just need to reduce the on rate by factor of 4, so that when the BioNetGen generates the network, it will multiply it with 4, because there are 4 binding sites, and then it will make the same total rate. I'm not sure I explained very well,
Sounds
but
like there isn't cooperativity modeling for the binding of calcium to calcium.
No, there is, because each of the rates is different. So
Well, he
he
just
made
said
4
that-
different rules. So
No.
there's a rule for binding 1 for the first one, the second
Yeah.
one, the third one, and the
yeah,
fourth one.
those 4
They
are
all have
different.
rate constants. I didn't catch that the first time, because the K-on underscore 0, 1, 2, 3, that's what distinguishes, that's what makes it cooperative.
Yes, there's a cooperativity in the system, but also, like if you do not add the symmetry condition and then use the variable directly, it gives a completely different result. Yeah. So I mean, if you start asking what is this over 4 or over 3 at the reaction rates, that's because of the symmetry.
There's a lot of different ways that this could be encoded.
Yeah. And actually, I'm going to show you when we get to the trimer phase, because at that point, if you try to generate the network, it will take so long. So just to save some time, especially from calcium, I will show you how it is done. Okay. So these first 4 rules are just calcium binding to calmodulin. There is no CaMKII in the system. Okay. And this 5 and 6 are calmodulin binding to the CaMKII. And if you look at it, you get a CaMKII molecule with no calmodulin on it. And it's totally unphosphorylated, or it is only phosphorylated at T286. And there's a calmodulin molecule with 4 calcium bound, and the CaMKII binding site empty. And then it will create this complex.
Can I ask you a question, Jan?
Sure.
For R1 through 4, you have assumed that the CAM the calmodulin is not bound to CaMKII.
Which one?
Yes, so calcium can only bind and unbind from calmodulin, but it's not
Yes,
bound to CaMKII.
yes.
So once it binds to CaMKII, it gets locked, the calcium gets
I mean, to bind it, it needs to have all calciums should be, I mean,
Okay.
all calcium binding
When
sets
it's
should be
bound, it
filled.
can't lose
Yeah.
calcium.
Yeah, when it is unbinding, it can lose.
So
That's,
that's an aspect of unreality.
Yeah, yeah,
yeah.
I guess. but-
Yeah, I-
Cooperative binding is an aspect of it.
yeah, I mean,
The difference in absurdity goes with that as soon as the any form of CAM binding. But you'd
Oh, I
have to
see.
completely change would be interesting to do. but
Yeah.
you'd have to
Oh, I
completely
see.
change the reality.
so basically you say if there's a calmodulin binds to
One
chem.
calmodulin binds, one calcium binds, and calmodulin can find a binding site, rather low affinity.
Mhm.
And then after that, all the other affinities are much, much higher.
For
Oh, I see.
calmodulin binding.
For
to
calmodulin
CaMKII.
binding, for calcium,
Oh, okay.
for calcium.
Oh yeah, yeah. Well, that's
Yeah,
that's what we
kind of
have
in-
actually. That's what we have also in this model. If you look at the affinities in the parameter block, like this 2.5 for the first binding, and then it's going up to like 88.25. So it's almost going like 40 times higher for the second binding, and
Well,
like,
affinity, yeah.
and especially if the 3 calcium bind, the fourth one is binding with a very very high rate compared to first calcium binding.
But the off rate goes up too.
Yeah,
But
that's right. No, it is actually.
But
It's
that doesn't, I'm
The
sorry.
third one is low, the second one is low, K off
That's
on two and K
Yeah.
on off two are low. Compared to the first.
well, actually, I mean, we are missing one thing. We are missing the symmetry also. For example, the first one is divided by 4, the second one is divided by 3, etc.
So that tells you that for free calmodulin,
Mm-hmm.
there's cooperativity for binding of the third and the fourth.
Yeah.
But that doesn't encode the fact, I'm trying to tell you what's missing. It's
Mhm.
okay, it's a
Uh-huh.
model, it's a
Yeah,
model, but
yeah.
what actually happens is that one calcium can bind to calmodulin,
Mm-hmm.
and that calmodulin, or even two bound
Mm-hmm.
calmodulin, can then bind to CaMKII
Okay.
with a somewhat reduced affinity,
Mm-hmm.
but it does bind. And then after that, when it's bound, the third and the fourth calciums bind at very high affinity.
Okay.
So there's a cooperativity between the binding of calmodulin to CaMKII and the binding of calcium.
Okay.
And
Mhm.
that actually affects the kinetics quite dramatically.
Oh.
So you'd
I
add
see.
additional rules for
Yeah.
calmodulin.
Yeah, you'd have to, you'd need a whole.
Mm-hmm.
So
Yeah.
this is a good candidate for entity
Yeah.
modeling, because we could just model, we could just, get the thermodynamics of the,
Yeah.
yeah. Yeah, yeah, I know, yeah.
I see. I see.
But you could write, you can write very
Except we
simple.
made one mistake.
Yeah. So well, I mean, the assumption in this model is only if all calciums are bound, all the calcium binding sites are occupied, then it can bind to the CaMKII. That's the assumption of this model. I mean, I'm not claiming it's right or wrong, but it simplifies a lot of things.
Actually, backwards to the-
Yeah. Okay. So I'm getting back to the rules. So we passed 5 and 6, which is this calmodulin binding to unphosphorylated and phosphorylated CaMKII. We're clear about those two. Let's get to the number 7 and 8, which is only unbinding event. But I'm not sure how I can show you all reaction. But this is a CaMKII molecule, which is totally unphosphorylated. And then it has a calmodulin on it. All calciums are filled, and then it also binds to the CaMKII. And then if you just keep going over there, you will see there are 4 different calciums over there. Okay, so it's a very big complex. It's only one CaMKII subunit. There's a calmodulin on it, and all the calcium binding sites are occupied. Okay, and this is the 2-step unbinding process that was explained on the paper. So it's actually in the first step, the calmodulin leaves, and then 2 calcium lives afterwards. That sort of unbinding event. And then there's this the rate is given as like a Michaelis-Menten type of reaction. And then if you look at the right-hand side of the equation after this arrow, we got a CaMKII with calcium binding site empty, and still the phosphorylation rate, phosphorylation states are the same. And then we have a calmodulin with 2 calcium on it. And then there are 2 more calcium free. And the off rate is defined as a Michaelis-Menten type reaction, which is the K of U rate. And if you get back here, it is a constant over 1 plus the calcium concentration over the Michaelis-Menten rate. I mean, well, if you are interested more, everything is on the paper, but this is how it is defined in the model. Yeah.
I'm curious, I mean, how is this different than explicitly, I guess, just writing out each
Oh, yeah, I see.
part of it?
I mean, it's not different,
It's not really
but
making
it's,
any
yeah.
Not making any assumptions about the rules that
Yeah.
help simplify the system.
Yeah, it's not, but the point is, I mean, this is just the Michaelis-Menten type, and then the parameters are given as Km and Kcat, so you're trying to use it as is, instead of trying to guess what is the forward and backward binding rate, because people give you Km value, and then it should be the forward binding over backward binding, right? But how you can guess what is the time step of this reaction? You have no idea, and at that point, it's better to use the Michaelis-Menten, right?
Where are you
there
doing?
a mathematical reaction to have calcium rebinding again?
Yeah,
Yes.
but it's not defined in this context. It's defined in a different rule. Okay, I just want to come to the nicer points. This rule 9 is the T305 phosphorylation. It's the basal phosphorylation. It has unbinding. There is no calmodulin in the CaMKII, and then both phosphorylation sites are unphosphorylated, and then the T305 site is getting phosphorylated. It's the basal one. But if you look at the parameters, it is 5 times 10 to the minus 4. It's very slow, and it's very, I mean, not unlikely, but it doesn't happen that often. And I just want to talk about the next 3 rules, because that's how BioNetGen could be very powerful to define that sort of ring structures or like that sort of long polymers. If you look at the rule 10, it has a CaMKII, and the calmodulin is bound with a calmodulin. And we don't write anything about the calciums because, as you remember from the morning, don't write, don't care type of thing. But I mean, we know that to a calmodulin to bound a CaMKII, it should have 4 calciums. Actually, this has 4 calciums on it, but we don't need to write it because it's already there. Is it clear? And then we have, this is our first CaMKII. It is unphosphorylated on both sides, and then the calmodulin is bound. And for our second CaMKII, this CaMKII also has a calmodulin, and then it's unphosphorylated. So this is phosphorylating with, one subunit is phosphorylated with its neighbor, and its neighbor is in CU state. The CU state is 2 unphosphorylated, T286, T305, but there's a calmodulin bound. Okay? And then as a result of it, the first T286 is getting phosphorylated, and the second one remains the same. You know, the second part did not change at all. It's the same with this one. But the first one is phosphorylated at T286 site. And if we get to the second one, we have the same. Let me do it like this. Yeah. So this CaMKII is in, again, CU state. It's UU, and the calmodulin is bound. And this one is in the in the P state. This is in the CP state because it's T286, and the calmodulin is also bound. Okay? So this has a different rate, R2. And the last one is for the DPU and DPP state, which are, so in the DPU and DPP state, the second one doesn't have a calmodulin, so the calmodulin binding site is empty. But the T286 is phosphorylated, and you don't care about 305 because it could be phosphorylated or unphosphorylated for this reaction. Is that clear from the rule? So basically, this T286 is phosphorylated by the effect of its neighbor. Basically, we are checking what the state of the neighbor, and then if the neighbor state is in one of our predefined versions, we are choosing the reaction rate based on it. And we have two dephosphorylation reactions. One of them is for 286, the other one is 305. And the last one is the T305 phosphorylation for pre-phosphorylated T286. It should not be 5. Yes?
I'm not completely clear why the CAM has either bang 5 or bang 4.
Oh, well, for example, this has 5, means that it's bound to this calmodulin. And this has 4, and it's bound to this calmodulin. So those calmodulins are different.
I mean, the each CaMKII has its own calmodulin.
Yeah. For example, the first one, first one is, I mean, I said 5, but it could be anything.
Okay.
You can give a number.
It's just a distinguisher.
Yeah,
Yeah.
a distinguisher. They are different.
Each bone has a calmodulin.
Yeah. So,
Can you use the lecture as well?
I'm sorry?
Yeah,
Yeah, you can use the ladder.
In principle, yes, it may be that we restrict, I don't remember if we restricted the mean space, but we never do. So we would never use a letter there, just by convention.
Yeah,
But,
in general.
yeah.
I mean, you can
In
use.
general, it's any
yeah.
label is allowed.
But you know, I don't know when I.
It's really just used to, I mean, it's not even, the 5 doesn't even have meaning across the arrow. So like you could if you wanted to make a confusing model, you could rename the bonds on the right-hand side, make them different on the products and the reactions. And it's only the graph structure that matters.
Okay.
Yeah.
And actually, you could read on the other side of the model, these bonds have different properties.
Yeah.
I can't think of any good reason why we would want to.
So maybe by binding something else, you change the interaction maps, so that shifts in the binding site.
Well, if you change the partner, you would be changing the bond. Yes, that would be different.
No, but let's say A, B complex, you are C, and then the interaction between A and B, that complex, another.
That would be a different step. That would be a different reaction. So if you're
Yeah.
writing it in a different reaction anyway.
Mm-hmm.
I mean, you're doing something afterwards.
Yes. So, well, are we clear about the reaction rules? I mean, it was fairly complicated scheme, and I mean, we can only define this one with 15 rules, and I think it's quite decent for that sort of system. Yes.
I have just one question before we shift to simulation. So the sequence in which you've written them down
Yes.
is set by some expectations about the pathway and iteration.
It's totally random. I mean, it depends on you. But I mean, you know, for example, if you want to bind, like, I mean, well, you can code them randomly, of course. You can just write this rule in the beginning, the other one in the end. But you know, when you're making the modeling, you start with from something simple, or like what is the ingredients, right? I mean, when you're cooking, you start with the simple things, and then you eventually make the food in the end, right? That's the same thing.
Yeah, but like this example is often given in this case, that if you take a book, right,
Uh-huh.
and you rotate it this way first and this way second,
Yeah.
versus if you take the same book,
Uh-huh.
do the second rotation first and the first rotation next,
Mhm.
you end up with a different result.
Oh, I see. Well, this is invariant in terms of the order of reactions. You can just give this one. I mean, it doesn't matter what the
Does it
order
make
of
the most
reactions.
likely
Yeah,
reaction?
because
It's
it
like that.
no, it builds a.
No, what is most
Well,
It checks all reactions.
oh, you're talking about simulation? No, this is building the graph structure, and the graph structure, everything is completely different. And in the simulation, it just looks for what are the possibilities, and then it creates the network, etc. So it doesn't matter. I mean, this is...
So this isn't saying anything about the order of reactions?
No, there is nothing. I mean, I gave the numbers R1, R2, and this is just for visualization
Just
purposes.
rules.
Yeah. I mean,
These labels are not actually used by the person.
no, nothing. I mean, you can, I wrote this R11, but you can just write something else.
That's for the humans.
Yes. It's a string. It doesn't read it. I mean, according to it, it's one single variable. And actually, this is the end of the reaction rules. And I mean, if you're interested, there are a lot of parameters in the system, and all these parameters have references in the paper. If you want to go to the supplementary, in the deep holes of the supplementary, you will find a text file, and then the text file has all the parameters and references. But there is one thing that I would like to tell you about, which is, in general, we always give the parameters in terms of concentrations, but if you are doing stochastic simulations or NFsim, it's better to define them in terms of molecules. So for that purpose, we are using this volume of the system and the Avogadro number just to convert this, especially the bimolecular rate constants, into the molecules units. And also, I would like to use all my species in terms of molecules too. So I'm converting them to the number of molecules also, instead of dealing with the concentrations. And let me show you the action block. It's quite short. So since it's a dimeric model, we can generate the network, and our simulations are way faster, especially the parameter scan. And I mean, you see this parameter scan at the end of the first session, but it's the method is ODE. The parameter is calcium input in terms of concentration, and it's from 1 micromolar to 100 micromolar. And we are scanning for 50 points in the log scale. And for this model, there is no phosphatase, so there will be no steady state, or there will be no condition that it will go to reach to a certain level, because eventually it will reach to 1 in terms of FP. But just to recreate one of the figures in the paper, I mean, they just make the simulations for 6 seconds, and they just check the value at the 6 seconds just to see the bistability. And I mean, I wrote number of steps, 1,000. You can play with this. But one thing, if you define some functions, and if you want to see these functions in the output, there is something called print functions. It's one of the variables. And it will also print out all the functions in addition to observables that you define in the system. Okay? And let's run this model. Hold on. So it's simulations, and run it. I'm sure my computer is way worse compared to yours. I forgot to save, but okay, now it's started. I guess you already got your results. Yeah, so uncheck everything, and let's look at the phosphorylation. You want to see the log scale. Yeah, you'll see that in the beginning there is no activity, but eventually if you increase the calcium concentration to a level around, let's say 10, you will almost get like 100% phosphorylated CaMKII. Yeah, so this is like a very simple thing that you can do with this model. Or there's another thing that I want to show, which is this, which is the 305 phosphorylation. It starts somewhere, and then around 10, it just makes a bump, and then it will get reduced to a lower level. And that's another interesting feature. Oh, no, well, basically, in the beginning, everything is checked. Okay, and then make sure that you uncheck all first, because there are a lot of things that we're printing out. And then go to phospho, for example, this is the first thing, and then change this x-axis from linear to log. Okay. So just after this point, I just want to, I mean, we know the model, we know what are the rules, etc. But the next thing that I want to show you is how we can model this as a trimer or a hexamer, how we can scale this up, how we can make this on a larger model. So I'm just going to open this one. I want you to follow me, because this is not on the website. So everything is same. Besides, when you are defining this CaMKII molecule, because if you want to build the ring structure, and if you want to, let's say, this will be your subunit, you need to make sure that your, what is your left and right neighbor. So therefore, in the previous model, we have only CaMKII, right? Only one CaMKII, but we got two CaMKII. And one of them is for left, one of them is for right. So basically, it denotes this is the binding site for my left neighbor, and this is the binding site for my right neighbor. And this can just translate through all of them. Yes?
But then it can just keep going around an infinite number in a ring. It doesn't know that it should have 6 in it.
I did not get that, actually.
Couldn't it become like a helix rather than a ring of 6?
Oh, yeah. Well, if you define it as 6, it will not get larger than that. Yeah, I mean, I will show you the rules. And well, it's in the seed species section. In the seed species section, when you are defining the molecule, if you close the loop, it will not get larger or smaller. Well, let me.
If you open the loop and you don't make any rules that change the binding states of the
Yes.
the CAM 6 left and right, then
Yeah.
it will stay the same.
Yeah, if you don't change the left and right binding, I mean, there's no rule about them. It's just predefined. You give everything as trimer, let's say, and then it will stay as trimer. No reaction is not going to change that structure. You will have this structure. And let me show you this.
So do you want us to change our model?
No. I want you to follow, actually. I mean, for instance, this is the trimer structure. You know, this is the first CaMKII. The left one is 1, the right one has 2, and then the second one has the left one is 2, right one has 3, and the third one has left has 3 and right one is 1. So basically it becomes a ring. And none of the rules are changing the structure, so this structure will stay the same. And the nice thing about this, if you want to make a hexamer model, you just need to write 3 more rows. And then it's the same model. You are not changing anything. Rules are the same, everything is same, but you only change the seed species. So it's.
And you can have the additional between ring binding site as well.
I'm sorry? What's that?
You can then add additional binding site for between the rings as well.
I mean, you could have, but I mean, it's not in the model and it's not defined actually at all. Yeah. But it, so, well.
Oh, I'm sorry, you have a binding, but I don't think there's a relation.
So let me show you the differences from the dimer model to this one. And the first one is, it is just for the ease, just for the simplicity, I just changed this calmodulin molecule. Because calmodulin molecule does not have 4 calcium binding sites anymore. I just changed this calcium binding as states. It has 5 different states. It has a calcium state. Oh, I'm talking about this. You know, this calmodulin. In the previous model, we got 4 different distinct binding sites for calcium. But now, I just remove all these binding sites, and then I just make sure that we have only one single state variable for calcium. It could be 0, means no calcium, 1 calcium bind, or 2, 3, or 4. So 4 calcium means 4 calcium bound. It's, I mean, For the graph structure, it saves a lot, especially if your model is getting way larger, because it brings up, let's say, if let's say each calcium binding site has 2 different states, right? So that will bring like 2 to the 16, 2 to the 4. So in total, it will just multiply the total size of the network by 16. But if you just define it this way, you will just save a factor of 4, because it will.
And then you add rules for the position?
Yeah, I mean, the rules are simplified now. Instead of having this 4 different calcium empty sites, you just change it to 0 state to 1 state, and CaMKII unbound with this on rate and off rate. But the difference is there's no calcium in the system now. So what I do is I change the on rate, I multiply it with the calcium concentration. Okay?
And you assume that there's so much calcium.
Yeah, that's the assumption. The amount of calcium is very large, and it's not changing at all. That's the assumption. Of course, it could be wrong if you are working with a very low calcium amount. But this is just to speed the simulation up. Normally, I mean...
It's really just going to speed the network generation. Well,
yes. Yeah, I mean, well, for trimer, I'm making the network generation. For hexamer, it's impossible.
It doesn't actually change the state count. Because you didn't have... You structured the rules before so that you had sequential binding.
Yeah, you're right.
But you still had states for calcium as well. whether it's
Yeah, but the main thing that I mean, those rules are same, R5, R6, R7, R8. I mean, they're very minor modifications because of this CaMKII binding or something. But the one that I want to show you is this T286. I mean, this R10, 11, and 12. It's the rules that Bayonet Gen, something nice, yeah. So basically, we have a CaMKII dimer. We are not interested in the trimer. We are just looking at the dimer portion of our trimer when we are writing the rules. Because we only need 2 subunits. We are not looking for the other neighbors. We only need 2 of them. And the first subunit has this CaMKII, and then it will get phosphorylated. And the second CaMKII is phosphorylating the first CaMKII. Okay? That's the same rule from the previous one. But the difference is, instead of one single CaMKII, the CaMKII left binding site, this one will get phosphorylated, and then CaMKII right one will be the one which will phosphorylate the other. So it's the assumption that the phosphorylation is going in only one direction. So basically, you are phosphorylating your right neighbor, and then your right neighbor is phosphorylating its right neighbor. So it's the unidirectional phosphorylation scheme that is explained. Yeah. Yeah, it's weird, but it's true. And I think, I don't know, it's 2004 paper from. Yeah, also the structurally, it's also visible. But the nice thing is, you don't need to define a trimeric structure. You don't need to define a hexameric structure to define this rule. And if you define this rule, it will find this pattern in your defined species, in the seed species block, and then it will apply to that rule. So that's the nice thing about Bayonet. And you can scale your model to very, very large sizes, like the hexamer, for example, which is impossible to write down the equations. And if you go to the 11, it's the same rule. The difference is, again, the P. And the next one is the same difference. I just need to make sure that I get everything back, because it will complain otherwise. I'm sorry?
Yeah, yeah.
I'm not sure. Can I backslash in the middle of a complex? I think it may not let me do it.
I think it's okay.
Because it should just continue the, but you put a
If
space.
you put a space in, that will cause a problem. But if you backslash and then go to the next line, it should be.
So you said.
That might or might not be.
Yeah, I mean, I'm not sure about the grammar also.
But I think the problem might be this, the leading white space there might cause a problem. Unfortunately, yeah.
Yeah.
Well, normally this is not a big deal. You can also set on a wrap mode in
Yeah, in the rule bender, yeah.
rule bender if you want to see everything.
But it's the same model, and I do the same thing, same parameter, scan. And let's see, if it complains, we can fix it. Well, it complained.
It's not happy with something.
OK, I got it back. So it says number 55. Oh, yeah. It's the first thing that I make.
All those periods.
Yeah. I'm not sure. Is there an? I think it's fine, but let's see. OK, this looks good. OK, no error. It's running. I mean, it did not put the console in a weird place. I put the console in a weird place. OK. Now we got our results. And if you look at it, it's similar to what we find in the previous case. But you know, this is dimer and trimer. The difference is minimal. And I finally want to show you how the hexamer model looks like. And it's exactly the same model, but the difference is this molecule. Oops. Yeah. So this becomes an hexamer now, just by playing with the seed species section. I did not touch one single thing about the rules or the other things, but just by changing the seed species, your ring structure is getting expanded. Or I mean, if you want, after this step, you can put another ring on top if you want. Like, for example, you will just define a new state for each CaMKII. And then it could have like the upper ring and the lower ring. And then you can just make a binding site between those two, so it will remain intact throughout the simulation. Yeah. Actually, I mean, there are newly, like new, not suggestions, but like someone is claiming that there are like this subunit exchange mechanisms in this CaMKII, and then these vertical dimers are leaving.
Incredibly slow.
Yeah, they're slow, yeah. But still, it's,
Days.
I think the data shows it's like minutes, but the number of CaMKII is very large, of course. And also the volume of the system. But anyway, I mean, this is how we can just increase the size of the system. But here we come to the last part. If you try to generate the network or try to simulate this with ODEs, good luck. Maybe 290 years or something, you can generate the network, and then you can see your results. But yeah, I mean, well, there's like a, they extrapolated, and then they find out it's with a Xeon 230 gigahertz processor, it takes like 295 years. But you can use NFsim. I get a very simple case. I mean, my computer is very slow, so I'm just going to reduce this number to 10. And the only difference is when you're simulating it, you're changing the method to NF. It's basically change it to NFsim. And you can run it. Well, the output is different. It doesn't do any network generation. You will not see the iterations. But it's running. You see the simulation time. And I only scan it for 10 points. Probably it will be like a, kinky lines. It will not be as smooth as the ODs. But still, it's running something. You will get a simulation of a system with this size. Still running. I'm not sure how long it will go, but
While it runs, I have a question about, you may have already answered that, but I think I missed it.
Yeah.
All the information. Here you have CaMKII left, where like all of the reactions, and you've ignored the CaMKII right side.
no, I'm not. No, I don't. It's only for 10, 11, and 12, because those are the interactions between two subunits. And then you need to choose one way. The left is phosphorylating right, or right is phosphorylating left, throughout all your system. Yeah, you cannot choose both way, etc.
Is the interface actually asymmetric?
What
How does
interface?
it know left and right?
It doesn't know. I just guess. I mean, it could be right or left. I mean, there should be two distinct binding sites. Not binding sites, two distinct neighbors for the ring structure. Each subunit needs to have two distinct neighbors just to make it like an hexamer or trimer. If it's a dimer, it doesn't matter, because either way, you got only one neighbor. But if you have a trimer structure and if you want to keep the ring intact, this is the way to do
But
it.
you have it going in one direction around the ring.
Yeah,
not
it's,
the
it,
other way.
yeah, I choose one direction and then I choose this. It could be, you can also randomize it maybe.
Well, you could make the two linkages symmetric. So you could just have CAM6, whatever, and not left and right, but have two of them.
But that's not.
It seems to be some use in the direction, but so it's not symmetric somehow. Yeah. But is it actually different residues that make the contacts, or is it just?
No, it's the way they are not facing outside.
I see. Yeah.
It's right out of structure.
Yeah.
Indeed.
Just to
It's done, right?
No, it's still running. But this is the last thing that I'm doing, so I'm done. Actually, who's coming next? Sanjana? Oh, Kunal? Okay, I mean, you can just come and start introduction if you want. I'm not sure how long this will take, but I just want to show you the output. No, my computer is super, super slow. I start a new one.
It only has to do 10 of them. It should happen.
No, it's quite slow. And also, like, toward the end of the parameter scan, the number of CalModulin is increasing, and then the binding events are increasing. That's why it's getting a little bit slower. But still, it's, live. I mean,
Yeah, the network free will slow down as the concentrations of molecules increase.
yes.
Because the number of events to simulate increases.
Indeed. There will be more CalModulin start interacting with the CaMKII, and then it will increase the simulation time, even if network free. But there's a picture that I don't remember where it is, but it will show how the network free. I think it's the Nature Methods paper. Oh, you show that, right? So it's still on the same scale. It's not changing.
Is it going to be an exciting file?
No. It's worse than the previous one.
It's going to be a little noisy, right?
It will be a lot noisy. But I just run the simulation from 0 to 20 instead of, 1 micromolar to 20 micromolar instead of 1 to 100. Because if you try to run it around 100, it may take way, way longer. I think we're almost done. Okay, 550. Okay, it's almost 5 minutes.